Hello, after a relatively long gap, we are back again. Welcome back to my channel and the ConQuiz series, ConQuiz-13. In ConQuiz-12, we promised that we will be delivering something on quantum. So today, concept booster on quantum part 1. Of course, we'll start this time not with rapid fire true and false type questions, but rather short conceptual questions. It would be maybe 2 or 3 parts. So today is part A of short conceptual questions. Okay, so let us start. But before going for short conceptual questions, let me start with a few preliminary, informative rather you can say, but very important questions. So let us start concept booster quantum part 1. First question: Einstein published 5 papers in the same journal in the same year. One of those papers brought him the Nobel Prize. On which work it was? In which year were they published? So sometimes I get answer from students that it is the relativity E equal to mc square, but sometimes I get the correct answer. So the year is 1905 and the paper was on photoelectric effect, not relativity. Okay. So the second question: the smallest possible value of a universal constant is named after the name of a physicist. Who is he or she? So it's a rather a trivial question, maybe, and it is Max Planck. We know the Planck constant, and its Joule second is the unit. It is denoted by H. Next question: energy is often expressed in terms of a quantity whose SI unit is meter inverse, length inverse. So what is that quantity? How energy can be length inverse, right? So it is, the answer is wave number. So meter inverse, obviously it is 1 by lambda, lambda is the wavelength. And how it comes actually? Assuming that E equal to h nu, and nu is the frequency, light frequency. So c by lambda, c is the light velocity. So E equal to hc by lambda. Now h and c are universal constants. So assuming that we are scaling up or down, we can divide a quantity by some universal constant, of course, and whenever it's needed, we can get it back by multiplying with that same constant, right? So here we are dividing by hc, product of hc. So E by hc is 1 by lambda. So it is a scaled energy. Whenever you really want energy in joules, then you have to multiply 1 by lambda, of course, by h into c. Okay. In spectroscopy, it is very important. The third question is a bit tricky. H psi equal to E psi. So general algebra says that you can divide both sides by h to get h equal to E. So any comment? The answer is h is not multiplicative. It's an operator, but not multiplicative operator. Rather, it's a differential operator. So you just simply cannot divide psi from both sides, right? So that is the comment. Well, psi, wave function, itself has no physical meaning, but a function of it represents a physically meaningful quantity. How? Actually, psi star psi product, we call it rho, and it is the probability density. What? Of finding the particle at a point, right? So rho is psi star psi, and of course probability density is something physically measurable quantity and meaningful quantity. Okay. Why rho is defined as psi star psi, not as simply psi dot psi? So why not just psi square? It's mod psi square, that is psi star psi. What is the answer? Well, psi in general, it's a solution of Schrodinger equation. So in general, it can be a complex function. For example, a plus ib. If you take psi star, then psi star would be a plus ib into a minus ib, right? And if you see that it is a real number, right? So a square plus b square, a and b are real constants. So it's a real number. psi star psi or psi star. But if you simply take psi square, then there is no guarantee that the product is a real number. Of course, if it's a physically measurable quantity, you will demand that that quantity would be mathematically a real number, not a complex. So that is the reason. It is due to Max Born. We call it Max Born interpretation of psi. Well, this is very important. Relate three quantities. One is simply rho, as I have defined the earlier question. Rho d tau is the volume element, small volume element, and another is integration over whole space, rho d tau. So rho d tau, integration rho d tau, right? They are not the same thing. So you have to relate properly. What is what? As we know, rho is probability density. Like mass density, mass by volume, mass density. So it is probability by volume is probability density. Okay. So if you multiply density and volume, we will get mass in case of mass density. So similarly, if you multiply probability density by volume element, it would give you the probability. Now probability at where? Not at a point, but in a small volume element d tau. So rho d tau, that means psi star psi d tau is the probability in d tau in small volume element. So if you sum up, integrate rho d tau over the whole space, that means you are adding up the probabilities of different small volume elements, and that would give you the total probability. So naturally it should be 1. So integration rho d tau is the total probability, rho d tau is the probability in d tau, and rho is the probability density at a point. Okay. And that's why you know that psi star psi d tau is 1. It's a condition. We call it normalization condition, and this is psi has to have this quality. That's why we call it well-behaved function. One of the quality of well-behaved function or acceptable function, right? Normalization. Well, so informative. Delta x delta px is greater than equal to h by 4 pi is one of the uncertainty relation. Then what is the other? So there are actually two. And another is delta E and delta T greater than equal to H. Okay. Well, this is a very conceptual and sometimes misleading concept that we bear. Einstein in his 1905 papers, one of the papers he published relativity, special relativity, where he used the energy is mc square or mc is momentum, so P into C, momentum is like this. On the other hand, in another paper, he started energy assuming that it's like wave and particle behavior, that is photoelectric effect. So H nu or nu is C by lambda, so H C by lambda. So they are written in red color. Pc is the energy. On the other hand, Hc by lambda is also the energy. So Pc equal to Hc lambda. Both are energy. You cancel C from both sides. So you get P equal to H by lambda. Okay. But it looks like the de Broglie relation, right? P equal to H by lambda. So my question is, can we call it the de Broglie relation? But all we get in 1905. De Broglie get in the 20s, right? Much later. So what is the fallacy? The relation, of course, P equal to H by lambda obtained by Einstein, but that is valid only for light. But de Broglie relation is a very general one. So P is H by lambda is valid for any damn thing in the world, universe, but Einstein gave only for light. So it is a philosophically curious question that why Einstein, even after getting P equal to H by lambda, he couldn't extend this concept beyond light. So that is a very important question, historical and philosophical question. Okay. So next question, in explaining the black body radiation, what new concept was introduced, which has no classical analog? So what was that revolutionary concept that Planck introduced? It is the quantization of energy. So quantization in a discrete way, not quantized. So that is the first time quantization concept was introduced, which was a peculiar at that time, rather ridiculous to some people, but even to Planck himself. But he has to accept this principle, quantization. Next, Niels Bohr, in his theory of hydrogen atom, used the same concept of quantization, but this time quantization of what quantity? That is the question. And as you know, class 11, 12 student knows that it is the angular momentum of the electron. So it is angular momentum. In case of Planck, it was the energy emitted from the black body. In case of hydrogen atom, it was the electron's angular momentum. Well, it's an operator question. G is AF, where A is an operator. What type of operator? Exponentiation. So e to the power something. Something means a function of x, say fx, and fx is given as ln x log x. So the question is what G is. Okay, it's a bit simple but tricky. So G is AF. Now A is exponentiation and f is the function is given ln x. So e to the power ln x is G. Now what is G? E to the power ln x. And more simply, if you take logarithm both sides, so ln G is ln x. So actually G is x. Okay, interesting. Next question, if A e to the power x is e to the power x, of course A is an operator, then give three different operator form of A. So what A can be? Of course A can be simply 1, multiplication by 1, it can be ddx or it can be even the second derivative, right? So these are the three answers for A. Next question, what do you suppose is meant by the zeroth power of an operator? Zeroth power, something to the power 0. So A to the power 0 is 1. That means literally applying A operator 0 times to F and leaving F unchanged. So it's quite obvious, but still. Well, another question from operator algebra, what condition, under what condition A plus B square is A square plus 2AB plus B square. Simply algebraic formula it looks like that, but there is a condition. How? A plus B square, okay, the answer is AB has to be equal to BA, that means A and B have to commute with each other. And how we get the answer? A plus B square is not just the formula, as we know, A square plus 2AB plus B square, rather it is the product of A plus B and A plus B. So if you multiply A square, then AB, then BA, then B square. So AB and BA. So if I want to write AB and BA as 2AB, then that must include the condition that AB and BA must be same. Then we can of course write A square plus 2AB plus B square. Well, under what condition A, B plus C equal to AB plus AC? A, B, C are all operators. Okay. Of course, linearity. It looks so obvious, but actually it includes a bit hidden lines. So let us explore. A, B plus C, the left hand side of this question, applied on F. So it gives you A, BF plus CF, but it's not obvious. It is the sum rule for B and C operator. Okay. And now, if A is linear, then only you can write A, BF plus A, CF. Okay. Now, BF operated by A and that gives you ABF. It is obvious, it looks so, but actually it's a product rule, as you can write that ABF is ABF, ACF is ACF, and finally the again sum rule of AB and AC. So AB plus AC applied on. So A, B plus C is AB plus AC. Okay. So it is justified. Well, another question that from operator algebra, complex conjugation A plus G wholes to the power star is linear operation. You have to justify our principles. So you have to know that what linearity means. Actually, there are two conditions. A, an operator, is linear if the first condition is A operating on F plus G two functions, it give you AF plus AG, and the second condition A operating on CF, C is in any constant, maybe complex, and that should be equal to C into AF. Sometimes we forget the second condition actually, we often focus on the first condition for so many questions, but that's why the question is given here, because you have to focus on the second condition also. How? Because exponent conjugation F plus G star, that is F star plus G star, no problem. That means the first condition is satisfied actually, right? But CF whole star, that is A on CF, that means conjugation. So CF whole star is C star F star, but CF is C into F star. So C F star on your right, but on your left it is C star F star. So in general, it's not true, it's not justified. Of course, if C is real quantity, then it's justified, but that's a special case. So in general, it is not justified. C has to be equal to C star. So here we see that the condition 1 is satisfied, but not 2. Okay. Give the kinetic energy operator T for a 2-particle 3-dimensional system. So kinetic energy, as you know, that P square by Tm, and P is the momentum operator, and that is h bar by I ddx. So P square is h bar by I ddx whole square. That means minus h bar square d2 dx2, and then by 2m. So minus h bar square by 2m d2 dx2. But that is for only x. But here it is a 3-dimensional, and energy is additive property, and x, y, z are independent coordinates. So simply the same term would come, as you know, and 2 particles are there. So one would be for the first particle mass m1 and the second particle m2, but the terms looks very similar. Del 2 del x1, del 2 del y1, and del 2 del z1. Similarly for delta second particle, del 2 del x2, del 2 del y2, and del 2 del z2. Well, so you have to remember that our energy is additive property, so we can add the terms, and x, y, z are independent coordinates. Well, now a particle in a box, PIB. Let us assume that's a cubic box, and the energy is given in such a way that 8 ml square E by h square is 12. L is the length of the box, and m is the mass of the particle. So the question is the degeneracy of the level. Okay. So you know what degeneracy is, that if a given energy level has more than one eigenstates or wave functions, then we call the level is degenerate. For degeneracy 1 or non-degenerate case, we can synonymously use that level and state, but in general, that's a common confusion of students. In general, level is energy related, and wave function or eigenstate is wave function related. Okay, psi. So here we will see that how many wave function are possible for this energy. So actually, if you rearrange the equation, E is 12 h square by 8 ml square, and if you compare with the 3-dimensional energy expression for PIB, you will see that actually this is a square sum of squares of 3 quantum number m, n, and k, all are integers, mind that, and that is as per the question 12. This is 12. Okay. So the condition comes out that m square plus n square plus k square has to be 12, and the only possibility is there, and that is all are 2. Why only? Because you can find thousands of m and k if you allow m and k to be any number, but not restricted to be integer only. But here they all are integers and integer only. So there is only one condition: m, n, k all are 2. Okay. Another one, but this time the value is 14, right? Degeneracy for this energy PIBQ. And here answer is not 1 but 6. How? Because again by same the rearrangement gives you this energy expression from this one, given one, and here the sum of the squares is equal to 14, and now you can check that that is possible if m, n, k are 1, 2, 3 independent. That means m can take up values of any one of these 3 values. Similarly, n and k, they can take up any one of the 3 values, 1, 2, 1. So if you rearrange 1, 2, 3, 1, 3, 2, 2, 1, 3, and so on, there are 6 possibilities. Why they are different? Because if you say 1, 2, 3 and 1, 3, 2, why they are different? Because the wave functions have the 3 quantum numbers m and k, and 1, 2, 3 is m and k, but 1, 3, 2 So n is changed, k is changed, so the wave function changed, but the energy remains the same. Well, yeah, this is a bit tricky question. This combination here, a combination of three wave functions, 151, 333 and 511, particle inbox problem. So this is a linear combination of three functions, and this combination is also an eigenfunction of the same problem. Is it so? Justify or criticize. So it apparently looks a bit difficult question, but it's a rather tricky question, but then simply you can catch the trick. What is the trick? There is a theorem involved here. You have to identify. First of all, the answer is yes, it is justified. And what is the theorem? Linear combination of degenerate eigenstates. Degenerate eigenstates of a linear operator is also an eigenstate with the same. So if this psi used in this combination, they are eigenstate but degenerate eigenstate, then only you can take a linear combination and the resultant combination is also an eigenstate. It is confirmed from this theory. Not only that, the eigenvalue of that new function is the same as those of the old three functions. Okay. So this is the theorem. Now for this particular problem, what you have to check finally is that whether this psi, these three psi, are they really degenerate? That means the energy associated with these three wave functions are the same. So the simple question is now you have to take the sum of the squares of 151, 333 and 511 and check whether the value is the same, because that is the energy. So as a matter of fact, these three summation are same and that is condition. So the corresponding three energy states, eigenstates correspond to the same energy eigenvalue of 27 unit. Okay. So of course you can combine them and get a new function which is an eigenfunction with the same eigenvalue. If the state function psi is given as root over 2 by L sine 3 pi x by L for a particular box, what is the possible value that results as measurement of energy? So again, apparently it starts with a bit ambiguity how you can find it. But again, it's a bit tricky in the sense that if you can identify that the given function is actually an eigenfunction, eigenstate already. So the measurable quantity is nothing but the eigenvalue. So if you can identify that what quantum number is associated with this wave function, and then you must put in the energy expression to get the eigenvalue, right? And that is the possible measurement value of energy. So can you identify? Yes, it is the 3. So n pi x, exact general expression is root over 2 by L sine n pi x by L, and it coincides if you place 3 for n. So it is a eigenstate for n equals to 3, right? So the energy expression gives you n square h square by 8 n square. So n is 3, so 3 square is 9. 9 h square by 8 n square. That is the energy value, and that is the probable or possible value of the measurement. Okay. From SHO, n equal to 25. Okay. So don't get perturbed. 10 is suddenly I'm taking 25. The sign of psi in the right hand classically forbidden region is opposite the sign in the left hand classical forbidden region. Justify or criticize. So if you carefully see the question, apparently looks a bit difficult one, but it is considering something very preliminary, the odd even parity of the wave function. And as you know that that psi, any psi, say psi 0, if it is, we know that psi 0 is even in case of SH, and also you know that psi n, if it is odd, then psi n plus 1 is even. That means they alternately come even odd, even odd, right? So psi 0 is even, so psi 1 is odd, psi 2 is even, and so on. So psi 25 is odd. So if it is an odd function, then definitely the left and right symmetry would be, minus of that, right? So that's why the question, it is justified that the left hand side and the right hand side would have opposite side. Okay. So it involves the concept only that odd even, whether the information you know, that odd even, this is the alternate way, and the psi 0 is of course an integer. So this much of information is needed only. So the last question, adding a constant C to the potential energy leaves the stationary state wave functions unchanged and simply adds the energy eigenvalues. Justify or criticize. So let us explore it. It is justified first of all. So H is the total energy Hamiltonian operator, and I am adding C. So now operator is H plus C. Now this is of course H psi plus C psi. Okay. Now H psi is E psi and C is a constant. So C E psi plus C psi. Now both E and C are numbers, so you can take common psi. So it gives you E plus C psi. So what we see that H plus C, the new operator operating on psi, gives you back some constant E plus C operating on psi, and E plus is nothing but the C is added to the energy. So yes, of course, in general we can add a constant term to the potential energy part, and it doesn't disturb at all anyway. It only gives that C is added to the total energy as well. So that's all from today's part. Thanks for watching, and I promise that my next video will come very soon, session 14, and that would be on quantum part 2. Again, short question type of answer, part B. Okay, so please keep on watching. Do subscribe. Encourage your friends to subscribe. Thank you once again.